Right. Well, I'm going to talk about a camera we're developing here at APL that will be useful for observing disturbed soil. Next slide. Right. So as we know, disturbances have been documented around pretty much all the landing sites as seen from orbit. Typically, there's sort of an inner and outer blast zone. These are seen either directly in reflectance images or in either temporal or phase ratios. Now, the cause of these changes is somewhat uncertain. It could be related to changes in texture, such as smoothing, perhaps compaction, destruction of the uppermost porous fairy castle texture. Of course, there's probably removal of fines, including perhaps the most highly mature uppermost particles. So how can we learn more about this? Well, let's look at the next slide. One thing is cameras on the surface, which certainly are useful, but for a typical RGB color camera, that the color itself is of pretty limited scientific, spectral use. This is because, as you can see in the plot on the left, that these filters are really broad and they have extensive overlap. So they make, beautiful job of mimicking the human eye and make nice images, but they don't capture the key lunar spectral variations, which you can see in the plot on the right that shows reflectance spectra for the major lunar silicate minerals. And you see how the three RGB channels are kind of bunched up there, and they don't capture variations, particularly in the band depth, the ferrous iron absorption feature that occurs between about 900 and 1,000 nanometers, which is key for understanding lunar composition. Now, there have been some, spectrometers sent to the surface. In the next slide, these are we're on the Chang'e 3 and 4 rovers and the Chang'e 5 lander. They had two different names, the Venus or LMS. But just to briefly summarize their findings, at Chang'e 3, one group concluded that the exhaust disturbed area, shown there in the upper right, is less mature than a minimally disturbed area a bit farther from the lander. Whereas with the Chang'e 4 rover, they did not see any clear changes in maturity along the rover traverse away from the lander. Now, Chang'e 5, that was a sample return lander, so it was static, and it had this sort of working zone down at the foot where it collected the samples. You can kind of see that work zone there in the figure on the bottom right. They didn't see any clear maturity differences between areas of the surface, which of course had been affected by the lander exhaust, and an area that they scooped to a couple centimeters depth. So there's interesting observations here, but we need more observations to help separate maturity effects from photometric effects. And so I think a good way to do this, if we go to the next slide, would be with a low-cost multispectral imager that we're developing here at APL with Dolly funding, called the Mahina multispectral camera. So this is a commercial off-the-shelf based CMOS imager, covers the visible to the near infrared. And we use a set of custom lunar-specific filters in a Bayer-like pattern so that we can obtain snapshot imaging. You don't need a filter wheel or scanning like you do with a hyperspectral imager. We'll employ 3 filters in those wavelengths you see there. Those are similar to the wavelengths on the Clementine camera and a number of subsequent lunar multispectral imaging instruments. That filter set allows for extraction of iron and titanium content, as well as the optical maturity parameter using algorithms that were developed by Paul Lucy and his co-workers. And I'd also point out that last year, Kevin Cannon defined a set of soil classes for resource utilization. And those soil classes can be mapped with this filter set. And the transmissions of those filters are seen there on the lower left. You can see how they're narrow and spaced at the key lunar wavelengths, unlike those typical overlapping RGB filters that you saw in an earlier slide. So let's get on to what the next slide says, which I think is some CONOPS that you could imagine for surface disturbance, plume studies, and so forth. So first up, if this was mounted on a static lander looking downward, then as several other instruments will, operate during terminal descent, we'll get calibrated multi-band, either video or images of the surface interactions, and having those clear, distinct wavelength intervals, I think would be helpful with say characterizing the particle sizes based on the optical scattering and so forth. If the instrument was mounted on a lander looking to the side, in other words, its main science goals had to do with the geology of the lander's surroundings. Still, you could probably turn it on towards the end and just observe any plume material that does happen to rise into the field of view. And then once on the ground, it can observe the proximal disturbed area and compare that with the optical maturity of more distant areas that are less disturbed. And then by making photometric observations, that is, as the sun moves and the phase angle changes, the data can be processed and with fits to Hapke models to extract parameters that are related to things like the macroscopic roughness angle, the scattering behavior of the surface, porosity, and so forth. And I think that's important ground truth for better understanding orbital data of a variety of geological processes all around the moon. Whether it's splotches, fresh crater ejecta, imps and pyroclastics, all things that we'd like to understand more about the nature of texture changes and how they show up in remote sensing. Rovers, of course, perform detailed studies along a traverse. A stereo version would be great because then you get co-registered DTMs, and you can imagine having different filters in the left and right eyes to give greater spectral detail. It's a pretty low mass, low power instrument, going to be on the order of 800 grams or so, including a thermal housing and its electronics, just a couple watts. And I'll just end up with a one slide that shows a bit of hardware. The next slide. Yeah, we're getting ready for proton single event radiation testing next month. The image sensor is just that thing about the size of a quarter over there on the left. And this instrument does have a heritage from the Vertex camera array on the Lunar Vertex Prism payload. So it shares some of the electronics heritage and so forth. That housing that you see there on the lower right is a cluster of three cameras for the VCA, and the base there is just about 3 inches. I can quit there. Thanks.